Okay, so day 2 momentum. So since momentum is a vector, if we have a two-dimensional collision, we have to look at the momentum in both the x and the y direction. So here's our question. We have a 2.5 kilogram blob of putty moving at 4 meters per second and a 8.5 kilogram blob of putty moving at 2 meters per second, and they hit at 90 degrees and stick together. So let's just label these first. So I have, let's call this M2, and this is our 8.5 kilogram blob, and our velocity is initially 2 meters per second. This other one, we have a 2.5 kilogram object, and let's call it M1, and it's initially traveling at 4.0 meters per second. So we have to recognize that the small one only has momentum in the x direction, and this big one only has momentum in the y direction. So different ways we can solve this. We can solve this using algebra, or we can also solve this using more visually, using triangles. I'm going to use the algebra method right now, though. So we're going to first look at just the x direction. So in the x direction, what's happening? So when these are going to collide, they're going to merge together, because in the question it says it's going to combine. So it's going to merge into some bigger putty, and we know it's going to move off somewhere in this direction. Somewhere in that direction at some angle theta. Okay. So I look at my scenario. I have M1, V1, and technically there's like this M2, V2 as well. But again, because that putty doesn't have any x momentum, that's just going to equal to 0. So that's going to equal to the combined mass afterwards. Let's call it M, and times some velocity V. But again, we're only looking at the x direction right now, so we need that component of velocity in the x direction. So we get cos theta. So we simplify this equation down. We get, if we simplify it down, we see, okay, well, let's actually fill in numbers first. We have 2.5 kilograms times a velocity of 4.0 meters per second. And that's equal to the combined mass of 11 kilograms times some unknown v and cos theta. So 2.5 times 4, that gives us 10. I'm not going to put the units in right now. Just it's easy to see when we have the equation with just the numbers, but technically we should have that units kilograms per meters per second right now. We're going to divide by 11 cos theta, and that is equal to our v. So all I did was divide by cos theta and divide by 11. So right now we have an equation. So here's an equation that we have derived. If we now look at the y direction, again, we have m1 v1 plus m2 v2. But in this case, the velocity of object 1 is only in the x direction, so we know that does not apply in the y direction. And after they combine, we get that total velocity times the velocity, so the total mass times the velocity times sine theta for that y component. So we end up with 8.5 kilograms times that velocity of 2.0 meters per second. And that is equal to that combined 11 kilograms v sine theta. Now it's just a matter of a little bit of algebra. So we're going to just plug in that 10, 11 cos theta where v is. So we have, well, 8.5 times 2, that's just going to equal to 17, equal to 11. And we're going to replace that v, we're going to substitute that v with 10, 11 cos theta. And there's still that sine theta. So you can see the 11s cancel out. So we get 17 is equal to 10. But sine over cos, that's just a trigonometric identity, tan theta. So we can see theta is equal to the inverse tan of 17 over 10, which is equal to around 59.5 degrees. If I now go back and plug theta, plug our value into either of our two equations. So for example, I can just plug it right in over into this theta right there, 10 divided by 11 divided by cos 59.5, we get 1.8 meters per second. So our final velocity is we get v is equal to 1.8 meters per second in the direction of 59.5 degrees. Normally we'd have some type of direction, so that would be, think of like north of east. What we can remember from past units is if we have exactly 3 vectors, we can make a triangle out of this. So what we can see is that momentum of object 2, P2, is going in that direction. P1 is to the right. So if we add these 2 vectors together, we get the resultant vector, P final, or P resultant, will just be that vector. So we can actually very easily solve for this as well. You see that, P2 is just going to be the 17 kilogram meters per second. P1 was just 10 kilogram meters per second. Then we can see that 17 squared plus 10 squared will be our resultant momentum. Just be careful though, you have to divide by that total mass. You want to find that final velocity. But you can also see right here, you get that inverse tan of 17 over 10, or if you want to solve for phi, 10 over 17. Now there's a second part to this question. So if we scroll down, it says, in the previous question, what percentage of energy was lost after the collision? So what you can tell is we're not talking about height or anything, we're just talking about the energy due to motion, so speed. So we're looking at kinetic energy. So if I look at kinetic energy before, so the equation for kinetic energy is, that's right up here, 1/2 mv squared. So initially, because energy is a scalar, so we don't care what direction things are moving. So I just say 1/2 mv squared, so m1v1 squared plus 1/2 m2v2 squared. So they're just plugging our values. So our mass of object 1 was the 2.5 kilograms times 4 meters per second, and we square that number. And same thing for the other object. We end up with 37 joules of energy. And then look at afterwards, later on. So before and after, 1/2 m1v. So in this one, we know our combined mass was 11 kilograms. And we found that afterwards, it is moving with a speed of 1.8 meters per second. And we're going to square that. So we plug this in, we get around 17.8 joules. So I think it's asking for what percentage of energy was lost after the collision. So the loss is the difference of the two. So we see, okay, originally we have, so percent energy lost. So originally we had 37 joules. Later on we have 17.8 joules divided by original. We get around 0, so you get 0.52. If we multiply that by 100, we get 52%. So we lost quite a bit of energy in that collision.